So we are living, say, with the consequences of Masque's theorem. So let's make a definition. Suppose you have mm, a number of representations from the same group, but to different vector spaces. Of course, the groups are all finite, and the VI are finite dimensional over C. Then their direct sum representation so you have several representations, say I ranging from 1 to k, and then you can construct a direct sum representation. What is this? Well, we may want to call it something like this, but this is just a symbol, and I'll tell you what this symbol means. So it's a representation of G, so it's a map from G into a GL of something. I'll fill this blank in a second, but eventually I want to go in the direct sum in the direct product of the GLs, which is a subgroup here. More about this in a second. Sorry, Zoom notifies me that my internet connection is unstable. If I miss you, then I'll get back as it happened yesterday and try and resume from the point when it was interrupted. And so this sends G, okay, to, well, it has to send this to an element here. And this is, or here, if you prefer. So this is the map that sends, well, oh, well, okay, let's say just plus. So this is where the VI are in the capital VI. As usual, since this is a direct sum, this will be unique. And what's this? Well, V1 to which you apply rho 1, because rho 1 sends, rho 1 of G is an element of GL V1, so you can apply this. Okay. And this means that if you have a rho I that sends an element G into a matrix of some dimension, okay, what you do with this direct sum, you send G to a big matrix. This is the same pattern that I exhibit yesterday, in which on it's a block diagonal matrix, in which you on the diagonal you have all the representation and zero elsewhere. Okay. Of course, here, no, sorry, this is not zero, but well, of the diagonal you still have something. Okay, and this direct product is represented by these diagonal matrices. I mean, clearly the determinant of such a matrix is the determinant of the individual matrices. So all of them are invertible. And so the resulting matrix is invertible. So it is in GL of the direct sum. Okay, so that's the direct sum representation. No, well, I want it to be in red because it's important. Okay. And why is this important at this stage? Because as a consequence of Masque's theorem, we have this important fact that every representation is the direct sum, in the sense that we just discussed, of irreducible ones. And irreducible are the simplest possible components, the ways of having a representation where irreducible. So remember that, remind the definition I gave yesterday, this is irreducible if and only if the only rho G invariant subspaces of V are the trivial ones, 0 and V, okay? But this is an analog of simple groups. In fact, yesterday I used also the term simple module for the group algebra. So what you can do with a generic representation is to split it up as a direct sum of irreducible ones. Because if it's not irreducible, Maschke's theorem tells you that you can split the vector space in the direct sum of two components without rho G invariant. And you keep doing this until you have to stop because the dimension is finite. So, I mean, every time you split, you lower the dimension of the components. This cannot go forever in a finite dimensional space, okay? And this is very important. As I said, okay, so a representation is determined by its direct factors, these irreducible ones. Perhaps this is a good way to note, this is an aside, something that is not directly relevant to the course, because the course is about, this course is about representation over the complex numbers. There are important chapters in the representation theory of groups that deal, for instance, with representation over the real numbers, or even representation over the rational numbers. This is something I'm not touching. But there is a whole interesting but extremely deep and complicated field which deals with representations over fields of positive characteristic. Because I mentioned C, the real, and the rationals, these are all fields of characteristic 0. And the point is, if you remember the formulas we used in Maschke's theorem, you need an average there, okay? When I use projection. And to average, so in Maschke's theorem, you build a certain map, C, which is 1 over the order of G, sum, and so on. Okay, and so you should be able to do this. You should be able to divide by the order of G, which is a positive number. I mean, if you are in characteristic 0, this is always non-zero. But if you are in positive characteristic, this might be 0. And a simple example is the following. Simple, but already tells you why things are more difficult. Suppose that take the field with 2 elements, okay? So this is 0, 1, the field with 2 elements. Let G be the group, the cyclic group of order 2. Okay? Then let V generated by E1, E2 be an F2 vector space of dimension 2. And of course, if I say that the dimension is 2, this means that E1, E2 is a basis, okay? And then consider the representation rho from G to GLV. Well, of course, you just need, of course, rho of 1 will be 1, as it happens with all representations being morphisms. And rho of G has to go to an element of order 2. And so we say that with respect to this basis, rho of G is, let's say, this one, okay? So essentially what it does, remember, my vectors are rho vectors. So here we have that the rho G sends E2 to E1 plus E2. This is what is written here. the first line is the image of E1, and this is sum of 1A1 plus 2E2, and it sends E2 to E2, okay? Well, just note that, of course, this element has order 2. I'll do the calculation here. But this is quite obvious. What happens if you do the square? You have 1, okay, this is 1, and then here you will have 1 plus 1, if you check, okay? This will be 1 plus 1, because it's 1 times 1 plus 1 plus 1 times 1. So this is 0, because we are in characteristic 2, okay? It's the field with 2 elements. So this is the identity, and so this element has order 2 indeed. So this means that, that of course, being in order 2, this mapper sends E2 to E1 plus E2, and conversely. Now you know that E2 is rho G invariant. This is written here. E2 goes to E2. Now, but now Maschke's theorem does not hold, because Maschke's theorem would tell you that there is a complement to the subspace, which is also rho G invariant. But this is an extremely small vector space. There's only 4 elements, and there are only two. There are only 2 other subspaces of dimension 1. Of course, I mean, the whole space has dimension 2. This is dimension 1. So if there is a complement, something, a subspace which make a direct sum with this, it has to be also dimension 1. 1 plus 1 is 2. And these subspaces are E2 and E1 plus E2, generated by, okay? And you see, we just saw that rho of G exchanges the two, okay? So that there is no other rho G invariant subspace. I'm out of space, but okay, I'll write it here. Sorry, but let's say I'll write it this way. E2, the subspace generated by 2, is the only one-dimensional rho G invariant subspace. And you see why Maschke's theorem does not work, because you have to divide by the order of G, which is 2, but the field with 2 elements, in the field with 2 elements, 2 is 0, so you cannot do this averaging. And the thing with the inner product doesn't work, because for that you need complex numbers and so on, conjugates, and so that doesn't apply. But I mean, you can see here that the fact that the order of G is 0 in the field forbids the use of this averaging method. So this would be the subject of the subject of modular representation theory. Okay, I'll rewrite it on the next page. Modular representation theory deals with representation over fields in which the characteristic divides the order of a group. Let's write this on the next page. So representations, linear representations of a group G over a field F with the characteristic of F dividing the order of G. Okay, and of course this has to be different from 0, because the order of G cannot be 0. What we are studying in our course is ordinary, this is called ordinary representation theory. Which means, say, characteristic 0. So the field F has characteristic 0, like the complex numbers, or in any case, the characteristic of the field does not divide the order of the group, so you can do the averaging trick, and the Masque's theorem works. Okay, so we will be doing just the ordinary stuff, not more. Okay. While seeing the proof of Masque's theorem, we saw that that projection psi had this property this property here, okay, which reminds you of a linear map, okay, because you can pull out this. This is not a scalar, but I mean you can pull it out. There is a definition going on here, because suppose definition, let V1, V2 be C vector spaces of finite dimension. This is understood. I mean, I don't think I will ever need the infinite dimensional spaces. If I do, I'll notify you in advance. So let this be the vector spaces, and let rho I from G to G Vi be representations, where again G is I'll stop repeating this eventually, but G is a finite group. Okay, then a morphism of representations. Okay, no, let's put it that way. Let's put it like this: a linear map F from V1, V2. Okay, so we start with a linear map. So it's a map that respects sums and linear combinations. Okay, if you say linear combinations, I've said it all. So a linear map, okay, is said to be a morphism of representations if for all G in G we have, and we write it simply in terms of map, rho 1 of G F equals F rho 2 of G. Okay, so this means if you look at in terms of vectors, that is for all V in V1 and G in G, you have that V1 rho 1 G, because this is a composition of maps, okay? Because this goes from V1 to V1, and F goes from V1 to V2, okay? So this composition is a map from V1 to V2, and so V1 goes to V2, and rho 2 of G is an element in GL V2, so this goes from V2 to V2. So the point is that this, if you apply F to this, you get this, okay? So it's similar to what happened with Masque's theorem, except that you have two representations, one on V1 and one on V2, okay? And so if you take, sorry, I wrote V1, but this is understood. So if V is an element of V1, you can apply rho 1 of G to it. Once you apply to, it's not V1, sorry. Well, we can write V1, but if you write, then if you apply F to V, you go to V2, and then you have to apply rho 2. So you see, rho 1 of G comes out of F, except that it becomes rho 2 once it comes out. Okay, so it's a linear map, so you can pull out scalars, for instance. If you have a lambda here and complex numbers, it comes out. But also these matrices, these images of rho 1 come out, except that they become rho 2 on the right. And the map C in Masque's theorem was an example of such a map. Okay, so we have already seen examples. So these are morphisms of representation. You can have also isomorphisms of representations. And well, but first, a rephrase in terms of modules. A morphism F from V1 to of CG modules. And okay, is a map such that is a, okay, let's say a linear map such that, well, it's the same thing. Okay, I'll write it like this. F, now I have to use some term, let's say tau, V tau F equals VF tau for tau in CG. Okay, so an element tau, it will be a linear combination of elements of G with coefficients, complex coefficients. And so the complex coefficients are already dealt with the linear map and even the sum. And so you're doing saying the same, essentially, that what's important here, the linear map, as I said, takes care of coefficients and sums. You're saying this, okay, for G in G. And the reason why sorry, I'll be back in a second if you have not written this down. The reason why you have row 1, row 2 here and not there is because this is understood. When you speak of a CG module, you have this understanding, and here let me use V1 and V2, that V1G is V1 row 1G, and V2G equals V2 row 2G. It's the same thing we do when we have vector spaces, because you can have completely different vector spaces, but you denote the action of a scalar. Let's say you have two completely different vector spaces over a field C, say the complex numbers. So you always write the scalar multiplication like this, V1 times, say, lambda, V2 times lambda. But of course, this operation could be completely different, okay? One could be functions, the other could be n tuples or whatever. And it's understood that they are different, except you use the same notation. With the raw notation, this one, so let me write it well, because my ones look too much like. With this notation, you see a difference, but with this, you understand that they are different. So a morphism of modules or a morphic representation are exactly the same thing. You regard in the same vector spaces once as object of a representation, and in the other case as modules. But the principle is the same. In this case, it looks very much like more like a linear map, except linear map means linear over the complex numbers, and here you have also the group elements switching from the left to the right of F. Okay, so this is a morphism. Of course, you can also have an isomorphism. But let's come back to the concept of isomorphism representation. So an isomorphism of representation is a morphism of representations. F from V1, V2, where we understand that we have the two representations like this, which is invertible, say. Okay, so it's a linear map which is also invertible. And then you see, so I'll be back here if you've not written the details. So look at this from this point of view, okay? We see that row 1GF is F row 2G. I'll copy it to the next page. So we have row 1GF equals F row 2 of G. But if F is invertible, this is equivalent to having that, no, okay, I'll write it the other, yeah, okay, I'll write it like this. Just a second. Yes, that row 2 of G, I prefer to write like this, will be F inverse row 1G, F, okay? So this is a map from V2 to V2, and here we are going, F goes from V1 to V2, okay? Row of G goes from V1, row 1 of G goes from V1 to V1, and F inverse it goes from V1 to V2 to V1. So you see, in the end, you get a map from V2 to V2. And so you see that row 2 of G, I mean, each individual element is conjugate to the individual row 1 of G. which is what happens when you change bases, okay? It's the same, exactly the same phenomenon. Okay, so these isomorphisms or representations is a natural concept, and it's similar to changing bases. Now we have a very important result, which is extremely simple to state and prove, but extremely powerful, here you will see, which is called Schur's lemma. This is something that, for instance, even, not even, sorry, for instance, theoretical physicists know very well because representations are important to them. And so they swear by this result. Isai Schur is the person who really invented the theory of representation and characters, which I'm going to introduce presently. And this says the following. Suppose you have two irreducible representations. And remember, these are important because if you have an arbitrary representation, then you can split it up as a direct sum of irreducible representations, okay? So these two representations will be as usual, rho I from G to GL VI, okay, for I equal 1, 2, okay? Let F from V1 to V2 be a morphism of representations. Then there are only two possibilities. Either F is 0, which means, of course, the map that sends everything to 0, or F is an isomorphism. Since an isomorphism of representations is a morphism which is invertible, or this means simply that that F is bijective, invertible or bijective, which is of course the same. Okay? So this tells you that if you have two irreducible, mind you, irreducible representations, we see that the general case is very different, that there are many more options. If you have two irreducible representations, a morphism between two of them can only be 0 or an isomorphism. And we see that even an isomorphism will have a very special type, but this will be a corollary. So let's see the proof. The proof is very simple because you consider two subspaces. So you have the image of V1, F is a map from V1 to V2, will be a subspace of V2, okay? And the kernel, this is in particular a linear map, so I mean you can consider a kernel which will be a subspace of V1. The kernel of F will be a subspace of V1. And my claim, we have already seen in part this in the course of the proof of Maskell's theorem. Claim these two subspaces, these are rho G invariant subspaces. Okay, and this is quite simple. Let's see the details. So let's try first with the image, okay? Because you take an element in the image, or I'll write it like this, though since I write the maps on the right, I should really, sorry, I should write, sorry, okay, let's do like this. I strike this out and I replace it with V1F, okay? Because I'm writing the maps on the right, okay? So this is what I should do. But it's the same, it's the image. So so we'll take an element in V1F. So V is in V1, okay? And you take G in G, and you take this, okay? Sorry, rho 2. Okay, rho I G invariant subspace is just, something in a second. Okay, so V1F is a subspace of V2. So to be invariant means to be invariant under rho 2 of G, okay? I wrote rho G invariant, but there is no rho here. There is a rho 1 and rho 2. And since this is a subspace of V2, I should look at rho 2 of G. But being a morphism means simply that you can exchange F and rho 2, except that when it goes inside, this becomes a rho 1 because this element is in V1. So it's rho 1 of G, which is acting, okay? And you see that this applies, this is in V1F, okay? It's an image under F of an element here. So this means that if you take an element in the image, you apply rho 2 and you take an element in the image. So this is a rho 2 G invariant, okay? So V1F is rho 2 G invariant. I'm making more precise what I wrote here. And as to the kernel, you say, but this is an argument we saw already in the proof of Maskell's theorem, but let me repeat it. So suppose V is in the kernel of F, and then let G in G, and we compute V rho 1 of G. I want to prove that the kernel is rho 1 G invariant because it's a subspace of V1. And so to see that it's in the kernel, I apply F. And it's the same principle here, except that we are reading from the right to the left. This is the same, no, well, sorry. So this is VF rho 2 of G. Recall, I mean, when F switches to the right, rho 2 becomes rho 1. When F switches to the left, rho 1 becomes rho 2. And the hypothesis is that V is in the kernel, so this is 0. And so this would be 0 because this is linear. So we have proved that the kernel of F is rho 1 G invariant. Okay, so what we've done, we have started with the morphism or representations. And this actually, what I proved here is a more general fact. So far, I haven't used the fact that the two are irreducible. And I've simply proved that if you have a morphism or representation, the image and the kernel are invariant subspaces of the proper subspace. This is where the approach via modules of the group algebra pays off, because I mean, if you have the group algebra, you simply say this is a submodule, okay? And the fact that we have two different actions is understood. Okay, so we have proved this. Now, let's use the assumption about irreducibility. And so by assumption, V1, let's say rho 1 is irreducible. Also rho 2, but we'll see this in due time. If rho 1 is irreducible, this means that for the rho 1G invariant subspace, kernel of F, we just proved that this is rho 1G invariant. There are only two possibilities. So the first possibility is that the kernel is 0, because to say, no, sorry, no, this is the second one. This is the whole of V1, okay? Because irreducible means that the only rho 1G invariant subspace of V1 are the obvious one, either 0 or the whole space V1. So this is one possibility. If the kernel of F is V1, this means F is 0, okay? because it maps everything to 0. So this is the first possibility, because I mean, here we have that there are two possibilities, either f is 0 or, okay? Good. And the other possibility is that the kernel of f is 0. Because just once more, irreducible means these two, V1 and 0, are the only subspaces which are rho G invariant, because the rho 1G invariant. That's good. So we are in this case. Now we look at the other end, by assumption again, rho 2 is irreducible. So there are two possibilities. For the rho 2G invariant subspace V2F, V1F. Okay, let me write it properly. The image, okay? So the first possibility is that V1F is 0. This time I'm doing things in the other direction. But you see, I have this, okay, that the kernel is F. So this means F is injective, okay? You remember this fact that if you have a morphism, to say that it's injective, it's enough to say that the kernel is 0. I mean, a linear map, for a linear map, you know this. Okay, so F is injective. So if the image is 0, since this is injective, this means that V1 is 0, okay? Because if you have an element of V1 which is different from 0, then it should go to something different from 0. So V1 is 0. And F is a trivial. Actually, I forgot to mention. Okay, let's do this. Let's say irreducible means that the proper definition of irreducible. I forgot to mention an important thing. Yeah, okay. Okay, let me put it here. I have forgot something in the definition of irreducible. Irreducible rho of G to GLG is irreducible if V is different from 0 and the rest. I forgot this to rule out this trivial case, because I mean, if you allow a subspace of the 0 to be irreducible, then I mean, it is the sum of 0 plus 0 plus 0. I mean, you have to rule this out. So this is impossible, okay, against the definition. This is a too trivial a case, okay, of a subspace 0, because this is a subspace every because otherwise you take any vector u and this, any vector space, and this will be the sum like this. So every space will be irreducible, okay, but this doesn't count as irreducible, okay. And so sorry, I have forgotten this to exclude this trivial case. So the other possibility, since V1 you see the image under of F is rho 2G invariant, is that it's the whole of V2. So this means F is surjective. Okay, and if you put together that F is injective and F is surjective, you obtain that F is an isomorphism, as F is bijective. So in an isomorphism. Okay, so I'm sorry for having forgotten this, but I mean, this is typical in mathematics. You give a definition, then when you use it, you notice that that you should add, you rule out some trivial case. Good, and there is an important consequence of this, in which, not exactly for the first time, but we will be using the fact that we are over the complex numbers, which of course have this important fact that they are algebraically closed, so every polynomial has a root. So this important corollary which will play a role immediately, we take a single representation, which is irreducible. And we assume that f from V to V is an isomorphism. Okay, so V will be different from 0. Then, there is a non-zero complex number such that a Vf for V in V is a scalar multiplication by lambda for V in V. So this tells you that an isomorphism of, we call sometimes an automorphism, because it isomorphism with itself, so out of self in Greek. So an isomorphism of V with V to an isomorphism of course of representations. As a very specific form, is just multiplication by a scalar, okay? Scalar multiplication. And the proof is once more quite simple, because you see, so F is a linear map, okay? Since C is algebraically closed, the characteristic polynomial of F has all its roots in C. But what are the roots of the characteristic polynomials? Are nothing else that the eigenvalues. So F has at least one eigenvalue, lambda, an element of C, okay. It will end up being C star after. Now note, we have assumed that F is an isomorphism or representation, but let's first consider the fact that there is a morphism. So what, the fact that F is a morphism means that F rho G, okay, sorry, if you apply F to V rho G, it will become VF rho G, okay, for G in G, okay? And okay, in this case, I mean, it's the same representation we have. We have just some vector space. There is no rho 1 or rho 2. What I really meant was the following. Because it's not F that is a linear map, but rho G is in GLV, so it's a linear map, okay? So being a linear map means that it commutes with scalar multiplication, for instance, okay? Rho G is a linear map, so if you apply rho G to V lambda, you get V rho G lambda. Sorry, I always make this mistake when doing this. It was correct, but it was not the point, okay? And then the calculation I really wanted to do is that if you do V rho G times F minus lambda, the identity, okay? This is V rho G F minus V rho G lambda, because applying this means multiplying by lambda. You can exchange this because of these properties. So the point is that you get VF rho G minus V lambda rho G. And so I get V F minus lambda 1 rho G. Okay, this time is correct, third time lucky. And what I obtained here, I obtained that Okay, you see, because I changed things here, but I'm exchanging f and rho g here and lambda and rho g there, okay? So this is what I get. So what I have here is that f minus lambda 1 is also a morphism representation, because you can see the rho g comes out exactly as here, okay? So what I obtain, so f minus lambda 1, which is still a map from V to V, is also a morphism representations. And remember, Schur's lemma tells you that a morphism representation is either 0 or an isomorphism. But since lambda is an eigenvalue of f, we have the determinant of f minus lambda 1 is 0. This is exactly the definition of an eigenvalue, okay? Because if you put x and indeterminate here, you get the characteristic polynomial, and lambda is a root. Eigenvalues are exactly the roots of the characteristic polynomial, so this is 0. So you have a map here, which is a morphism, and it's either 0 or an isomorphism, or an isomorphism. But it's not an isomorphism because the determinant is 0. Isomorphism means invertible. So f minus lambda 1 is not invertible bijective, because of course this would have meant a determinant different from 0. So it's not an isomorphism. And so this means by Schur's lemma, f minus lambda 1 is 0. Because Schur's lemma gives you a very simple alternative. An isomorphism between irreducible representations, and I trust I had, yes, irreducible here, is either 0 or an isomorphism. It's not an isomorphism because the determinant is 0, so it has to be this. And so you see, this is exactly equivalent to say that f is scalar multiplication by lambda, which is the claim we had, okay? There is a lambda such that vf is equal lambda v. And f is scalar multiplication by lambda, vf equal to lambda for v in v. Okay, and this lambda, you see an eigenvalue. So you see that really f as a matrix is just the diagonal lambda times the identity. Okay, so lambda is the only eigenvalue. So in the end, a posteriori, lambda is the only eigenvalue of f. Okay. And we will put this to fruition in a second, okay? So what we want to do, well, okay, sooner or later, but it will be next week, we are going to define these characters. As I said, characters are a very economical way of consider representations, because a representation is in principle, if considered, for instance, this representation here, if V has dimension n, to every G in G, you associate an n times n matrix, so you associate n square numbers. And characters allow you to represent to completely describe a representation by associating to every element of G a single number, okay? So you may have a representation of dimension n with n very large, but it suffices to have a single function from G to the complex numbers, not n squared, to describe the thing. And characters have important properties with respect to certain scalar products, and we will now investigate where these properties come out. Essentially, what will come out is that characters are an orthonormal basis of a certain vector space. And this will be, as you will see, a tremendous usefulness. So let's see where these properties come out. First, there is a lemma which we really saw already as seen in Maschke's theorem. And the lemma is says the following: let rho I G to GL VI be two representations for the same group G. For I equals 1 and 2, okay? Two representations. And let F from V1 to V2 be a linear map. Just a second. So this is a linear map, but it did not to me a morphism or representation, because it simply respects, okay, the sum and multiplication by scalars, but it does not respect necessarily the action of the ROI. But there's a simple trick, the trick in Maschke's theorem, in the first proof of Maschke's theorem, that guarantees that you get a morphism or representation. Then, formula to be filled here is a morphism of representations V1 to V2. How do you do it? Is an average, except that you don't need to average. So these maps will be called F prime, nothing to do with derivatives. And you don't need to average here, because I mean, in Maschke's theorem, you do an average because you want to end up with an idempotent. So a map psi such that psi squared equals psi. And then you need the average. But in this case, you simply sum over G, rho 1 G inverse F rho 2 of G. And this is a morphism representations. The reason why this is a morphism representation, the proof is the same, exactly the same as in Maschke's theorems, as I said above. So you take V rho 1 K, say, you apply F prime, and then you do the change the variables under which over which you are summing things, and it will end up on the right. You simply take Maschke's theorem and redo the proof and proves this. So this is a very important fact, that you can start with any linear map you please, and by doing this, say averaging, except that I'm not divided by the order of G, you get a morphism representations, okay? And so we'll start this chapter, say, which goes under the name of orthogonality relations. Actually, the standard orthogonality relations hold for characters. I mean, you'll hear about characters next week. But we're also obtaining some so-called orthogonality relations in a second for in a more general setting. And the setting is the following: proposition. Let rho I, this is a trend today, be two representations of G. And by this is obvious because I had two, but I is one of two. Suppose they are not isomorphics. Okay. For simplicity, we will take, let V1 and V2 be the spaces of row vectors. Remember, since my maps are on the right, vectors are row vectors with bases. There are two different bases because these are two different vector spaces. The first one will be U1, 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 UN, and the second will be V1, VM. Okay, so this is the basis of V1, and this is the basis of V2. Okay. More notation. Let rho I jk of G denote the jk component of the matrix rho I of G. Of course, with respect to this basis, okay? We have basis, so we have components. So this is a matrix, for instance, rho 1 of G would be an n square, n times n matrix. And so you have n square of this. Rho 2 of G, which would be an m square matrix. And so you have what you have. Well, then, for all J, S, T, and L, for all indices, which will be run in a way that we'll see in a second, you have that if you sum over G, rho JS, G inverse, rho 1, rho 2, let's see, TL of G, this is 0. And of course, I mean, since this is rho 1, it means that J and S will run from 1 to n, because they refer to rho 1, whereas T and L will run from 1 to n. But this is understood. I mean, I won't repeat it further later. Okay? There is a remark about orthogonality that I will make later. Okay, so this is a sort of an orthogonality. It tells you if you do this sort of scalar product. Well, okay, let me make the remark now. Okay, so before I go into the proof of this, let me make this important remark why this is called the orthogonality. So remember that we may assume the remark. Remember that I've shown at the beginning of the course, and then used in the second proof of Mashkev's theorems. Remember that we may choose the two bases so that the two representations are unitary with respect to, say, the standard inner product. Or say, I can choose an inner product such that the two representations are unitary, and the two bases will be orthonormal bases with respect to the inner product. So what does it mean? So for instance, let's do it with rho 1, because this is what we need. Yes, so if the base is the first base is U1, U2, well, okay, fine. If U1, UN is chosen like this, okay? And so this means let X, Y be two row vectors. So element of Cn be two row vectors with respect to this basis. Okay, then the inner product, the standard inner product will be, okay, these are row vectors, will be, let's say xy, will be x conjugate times x, times y transpose. Okay, this is a transpose. So if we take the standard, the standard assumption that a vector x as component x1, well, I should write an exponent, but okay, xn, okay, then similarly for y, then, okay, since it's similar, I will write it. Then this is simply the sum for I from 1 to n of xi conjugate. Of course, this is a conjugate, complex conjugate. Okay, and times yi, okay? So the transpose is because in terms of vectors, I have here the row vector x transpose and so x conjugate, and if I transpose y, which is also a row vector, I obtain a column vector, so I can multiply them, because I mean you can multiply this row by this column and you get this. Okay, so you have this. So if you have chosen the basics so that the two representations are unitary, in particular you choose row 1, this means so row 1 of G unitary means that okay, means that say let me use V rho G W rho G equals VW for yes, I did something like that already yesterday for all V and W, and now there is a concept of yes, I went through this yesterday, of an adjoint. Okay, so what we have here, yeah, we have that this adjoint is nothing else than the inverse of rho G. Okay, because this we discussed already yesterday. But what's the adjoint with respect to this scalar product? Well, so the adjoint it goes like this. You have this. You have this a matrix, an n times n matrix, and there is a unique matrix A star, which is the adjoint, which guarantees that you have this for all xy in Cn. Okay, that's the definition of the adjoint. I mean, this is a linear map in X, so it can be represented like this. There is a representation here. But I mean, this product is defined like, so the product, okay, this is represented as X conjugate times YA transpose, okay? This is scalar product. But this means X conjugate, and the transpose, as you know, reverses the order of products. And you can write it like this, a big conjugate. So if you take the transpose away inside, you will have to conjugate it, okay? And what's this? This is exactly XA transpose Y, okay? The scalar product. Okay, because it's the scalar product of the conjugate of this vector times the transpose of this. And so you see that A star is nothing else than the conjugate transpose. Okay, so we had seen that since these are unitary, the adjoint of rho of G is its inverse. So we have obtained that rho G inverse is going to be rho G transpose inverse, conjugate transpose. Okay, so this is the fact that we have found. I mean, no doubt you knew this very well from linear algebra courses or functional analysis, whatever. Just a second. Okay. So this is important because if we wish, we can rewrite this as, let me copy this and bring it over. add to library, and then we'll go to a free page. And this should be just the pictures, the last one. Okay. No, but how do you, just a second. Ah, no, yes, I simply bring it here. No, this is not the right one, sorry. This is from another course. Okay, and we'll put it here. Okay, so this can be rewritten. This is the JS component of the conjugate. So you can rewrite it as what? Since, as I said, rho G inverse, which is rho G inverse, you can put the inverse inside or whatever, is rho G transpose conjugate, okay? So this is the JS element of the rho 1 G inverse. So this is the Sj element conjugate of G, okay? And so you see that this is exactly the scalar product, except that the summation is doing over G. But let's say more details later, but this is the scalar product. Well, okay, doesn't matter. We'll have a scalar product. It looks like a scalar product, okay? Except that I'm summing over G. The index is over G. But proper definitions about this in a while. So, okay, so we are committed to proving that under these conditions, okay, this is zero. So how do you do that? Well, it's a relatively simple calculation. Let's see whether I'm able to do it without mistakes. Okay, so proof of these first orthogonality relations. Okay, so we are exploiting this important fact that if I take any linear map, then this will be amorphism representations, okay? Good. Okay. So, just a second. I forgot an important point. Okay, sorry, I forgot an important point here. To irreducible representations. Okay, so they are not isomorphic, but they have to be irreducible. This holds for irreducible representations. Okay, we'll see what happens in general. So I've added irreducible here. Okay, so the dilemma I just showed you tells you that if you choose any matrix from, any linear function from V1, V2, then you do this averaging trick, except that you don't divide, and you get a morphism representations. And then I'll consider, let EST be the linear map from V1 to V2, which maps so the basis here is U1, UN, and here V1, VM. This does the following, sends UI to 0, with one exception, that US is sent to VT, okay? So S, of course, runs from 1 to N, and T runs from 1 to M, okay? The dimension of V1 being N and the dimension of V2 being N. So as a matrix with respect to this basis, this is a matrix that is 0 everywhere, except that in the S row, it will have exactly one entry different from 0, which is the teeth, okay? And all the rest is 0, okay? So it's a standard matrix, matrix with just one. Because I mean in this representation, the est row represent the image of the est vector of the first basis with respect to the second basis, and you just have VT, okay? And then you compute this particular map. Well, okay, and then we know that if we compute this, this will have to be 0. Why? Because by the lemma, this is a morphism representation. So we have, because this map here is a morphism representations. And I'll continue on the next board, but I'll leave you time for writing this down. So this map, okay, is a morphism representation. The lemma that so the averaging, say, you get a morphism representations, but with the condition that I just added, that the two representations are reducible. Schur's lemma tells you that a morphism representations or two irreducible representation is either 0 or an isomorphism. My assumption is, let's go back, is that these two are not isomorphic. So the only chance for a morphism between two irreducible representations is to be 0, has to be 0, okay? Plus Schur's lemma. So this has to be 0, okay? We know automatically because it's a morphism representation, the two by assumption are not isomorphic. Then I'll consider also the case when they are isomorphic, and then it's slightly different. Good, and so let's see what does this tells us. Okay, so let's consider what happens when I take a uj, an element of the basis of V1, and I apply to this one of the summands of so this is, I'll be back in a second. This is just one of the summands of this. Then we'll sum over G to get this, okay? So what happens when you do this? Okay, so you have this matrix, and remember that the matrix rho G inverse has components that are rho JK, rho whatever, AB, okay? So the components of this matrix, the AB component, I have denoted with rho, I mean, the index is already taken by rho 1 and rho 2, so I use an exponent, but to denote the AB component. So what's this? This is the image under rho 1 of G inverse of the jth basis element. So it's its coefficients. So this will be okay, a sum from I, from K, say 1 to n, because this has dimension n. Okay, of what? We'll build it in stages of the UK. Okay, with coefficients the jth row of this matrix. So rho 1, JK, G inverse. Okay, this is just a linear algebra. This is a matrix which has these components. This is the jth basis element. So the coefficients of this will be the jth row here. So J indicates the jth row, and this is the index of the column. And then EST, rho 2 of G, okay? But now what happens when you apply EST? So that's the first step. I have computed this. And then I consider the next step, which means considering, well, no, say this, okay? And you see, EST is a very simple map. It sends everything to 0, except that it sends US to VT, okay? So when you apply EST to this, only US will be saved. okay? So there will be only one term which is non-zero, and this will be the term with US. Let's do it in 2 stages, okay? Because all the others are killed by yes, and this will leave you with JS, G inverse, okay? Because all the other are killed. EST kills everything different from US. But then, let's go up again. But then EST sends US to VT, VT being one of the basis vectors of V2. So you obtain rho 1, JS, G inverse, and then VT, because this is what US EST does, okay? You send US to VT, and then you have rho 2 of G. But here it's the same thing again. I'm applying to VT rho 2 of G, and this will be a sum for, okay, let's say L from 1 to M of what? Well, I have this. And this is this will be a linear combination of what? Of the VL, where the coefficient will be the coefficient of the nth row of rho 2 of G. Okay? Let me just a second. No, yes, sorry, of the tth row, okay? So tth row L of G, okay? So same thing. So this goes to this part. This sum, I have left this term of this one, okay? And in front I have this element here, okay? So VT rho 2 of G is the sum of the VL with coefficients that are the tth row of rho 2 of G, okay? And okay, so this is not exactly this. I mean, I applied this, which is just one summand of this, and now I sum over G, and I will get 0. Okay, so let's see whether I have enough space here to finish. No, I'll copy this and okay, let's sum over G. So if I sum over G, this will get 0, okay? Because this is this applied to UJ, okay? So I've seen that this summand equals this, okay? So I'll exchange this to summation. There is a summation over G, a summation over L. I can safely exchange them. And here I will get sum G in G of rho 1 JS G inverse rho 2 TL G VL. So this was the sum over L. I sum this over G, exchange the two because I mean, I can do it safely. And now what's the point? The point is that I found that this is 0 because I mean, this operator, if I sum this over G, I get 0 by Schur's lemma. And so I got this, and this is a linear combination of basis elements of these objects, okay? These are the coefficients. So this object here is the coefficient of the nth basis vector. But of course, if the vector is 0, and this is written with respect to the basis by the properties of the basis that are linear independent, it means that these coefficients are 0. So what I obtain exactly what I want, that is sum G over G, rho 1 JS, G inverse, rho 2 TL, G is 0. okay? Simply because the basis elements are by definition linearly independent. Okay, so this settles this first thing, okay? And now let's just state, because I'll split this proof in two, I mean, of the second result. So let's just state the result that I want to prove next time, which is the other half of this. And this time I will say, let rho from G to GLV be a single irreducible representation. Okay, and let V be the space of row vector at basis U1, UN. So this time I have just one, just one basis, and I use the same notation with the rho, J, so on. Then for all indices, this time they run from 1 to n, because there's only one thing. I take this sum, I keep calling average, but is not an average. Okay, so this time I don't write G inverse, but I write this transpose inverse. But this time it can be 0, we'll see why. But otherwise, if, so say otherwise, but this is something different if J equals L and TS equal T. Well, okay, I should write it in the other direction. So if the indices are the same, if the pair Sj is equal to the pair TL, then this is not 0 and will be order of G divided by n. Okay, so n, yes, so the dimension of V is n, because this is a basis with n elements. So this is slightly more complicated. We have a 0 if the indices do not match. But if the indices match, and the fact that I'm writing here a conjugate is simply because of this transpose conjugate, then I'll get something definitely different from 0. And this will come again from the corollary to Schur's lemma. But I think I might stop here and give the proof next time, once you have had time to see today's proof, so that you'll see that the proof of this is more or less the same, with just a tiny difference. Because in the previous case, in the previous proof, we knew in advance that map, that morphism representations was 0, because I have two non-isomorphic irreducible representations, Schur's lemma. This time, this is an irreducible representation, so there are two possibilities. A morphism representations can be 0 or a scalar multiple, or a multiplication by a scalar. And we have to tell apart which is which, but this won't be difficult. Okay, that's all for today.